Welcome to the 24th and final lecture in the Joy of Math series. In the previous 23 lectures, hopefully you've seen how mathematics was developed. Various branches of mathematics were connected, and in the interesting comments and history of the various men and women responsible for the development of mathematics. We've also looked at, briefly, how and why certain things work. And I hope that this type of information will possibly lead you to look into other aspects of mathematics, be they more history or more development of the mathematics, or even looking into learning new mathematics or relearning mathematics that you failed to understand the first time, but now feel very strongly that you understand the basics behind what was taught in the past. In this particular lecture, I'd like to do a few things. The first is to look at a very special situation to allow us to look at how our number system works. The second is to review the various branches of mathematics and some important facts about each. And then finally, to examine personal attitudes about mathematics, something of which I am greatly concerned. But first, an interesting question. What if the earliest human beings had been born with only 8 fingers, that is 3 fingers and a thumb on each hand? And when they learned to count, we'd have 1, 2, 3, 4, 5, 6, 7, 10. There's no 8 and there's no 9. 10 would be what we would call 8 fingers. How would this change our mathematical system? Let's take a look at the multiplication table for this base 8 or 8-finger system. At first, you notice nothing very strange until you get down to 2 times 4. And again, the numbers along the top and down the side are the numbers we're multiplying. The answers are in the interior. Notice that 2 times 4 is 10. Well, that makes a great deal of sense because the first place value is the ones place, and the second place value, which would still be called the tens, is what we would call the eights. And of course, 2 times 4 is 0 ones and 1 8. And notice that 2 times 7 is 16, and 6 times 3 is 22. And you might be laughing or saying this is confusing, but actually, if we only had 8 fingers, this would be what you'd know. And indeed, a system such as what we use with 10 digits would be confusing and in fact be laughable. And when someone said 8 and 9, you would find these humorous names for non-existent numerals. Let's go back to the table and look at some interesting things, because I'm always looking for patterns. And I think, to me, one of the things that mathematics teaches us is to look for and to analyze patterns. The largest 2-digit number is 77. And of course, notice 77 is not in that table. Just as 99 would not be in a multiplication table of 1 through 9 times 1 through 9. And of course, 77 being the last 2-digit number, the next number would be 100. And of course, that would be correct. It wouldn't be equal to the 100 in our system. It would have 0 ones, 0 8, and 1 8 squared. And in fact, that 100 would be equivalent to 64. Notice, for example, that the last number in this multiplication table is 61. 7 times 7 is 61. That is very relevant to our number table, because in our multiplication table, we'd have 9 times 9 equals 81. Notice they both end in 1, and the tens place digit is 1 less than the largest possible digit. That is, 1 less than 7 is 6, 61 in our 10 number system. 9 times 9 is 81. 8 is 1 less than the largest digit, 9. For example, look at the even numbers. Numbers that are multiples of 2, 4, and 6. Are they all even? And indeed, the multiples of 2, 4, and 6 all end in 2, 4, 6, or 0. Obviously, nothing ends in 8 because there are no 8s. But look at the multiples of 3. The multiples of 3 in our number system, when you add the digits, they always equal 3. Is that true here? And of course, if you look at 3 times 3, you see 11. And 1 plus 1 is not equal to 3. So some things break down and some things stay the same. And a mathematician would look at this and say, let's examine which things work the same and which things don't. And can we look at another multiplication table for a different base system and predict which rules would work and which rules would break down? That is what mathematics is, looking at a new system and determining what is the rules of operation for that system. Now, why would anyone in his or her right mind want to inspect a number system with a different base? And I guess before I became an instructor of mathematics, I was a student. And in one of my earliest experiences where I felt a learning experience really had occurred beyond what I was learning in the classroom was when in 7th grade I took French. That was the first foreign language I took, although living in Brooklyn, New York, to many people, English was a foreign language. But in French, I learned about grammar. And for example, I learned about the participle. Now, I had no idea when I was in 7th grade what a participle was. If you asked me, what is a participle? I knew what they were. I used them in my speaking and writing. I understood inherently the rules of their use. For example, well, not ending a sentence in a participle. But I never had thought about their meaning until I learned French. I learned a different language and had to learn the grammar because I was not used to the language. And by doing that, I learned more about English probably than I learned about French. Now, indeed, my belief is when we sit down and actually work with a different base number system, we begin to question things that we didn't question in our inherent learning of our decimal system. There are many things we do without thinking, which is fine, except when you want to generalize, when you want to utilize that knowledge in new contexts, you may get stuck because you truly do not understand what you're doing. And I believe that is very much true in the way we learn mathematics. We typically learn fractions and decimals as if they were separate from whole numbers. Algebra as if it was separate from arithmetic. I hope that in some of the examples I gave you in early lectures about arithmetic and algebra, you saw the connectivity between these two branches of mathematics. And I'm sure you recognize the connectivity between arithmetic, algebra, and geometry, because indeed that is something I believe was emphasized as we talked about geometric applications using algebra and arithmetic. Learning the rules of this other language, in this case the rules of the language of mathematics base 8, would be helpful for us to really truly understand, not just to use, but a much higher level of knowledge to truly understand and to be able to apply and to create new uses for our mathematical system. Now, imagine, if you will, if we had ancestors, or the ancient people who were the first humans, who had 12 fingers. In fact, I once dated a girl, this is true, hard to believe, whose mother was born with 6 fingers on one hand. There was a tiny extra pinky, which was surgically removed. But imagine if our ancestors had had 12 fingers, 6 on each hand. We would count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2 more sounds, and then 10. And if you find that distressing, if you find that confusing, of course. But if we were that way, then you would laugh at someone who only had a measly 10 digits in his or her number system. So the idea is looking at different systems and creating these things helps us truly understand the mathematics with which we work. Now, it is the same thing with mathematics in general. We need to persevere. There are some areas of mathematics, quite frankly, that are quite difficult to understand when you get into abstract areas. And in many cases, we need to learn this for an educational situation or to be able to apply that abstract mathematics in a real-world environment, be it finance, science, engineering, what have you. And I just believe that the more we understand about the basis of our system, the arithmetic, the better equipped we are to handle the more abstract, the more advanced, the more difficult. Just because something is difficult doesn't mean you can't do it. But if you believe you can't do it, then unfortunately you're right. Hopefully, our tour of the beauty and the function and the history of mathematics has allowed you to see that people who have fears about mathematics, who have beliefs that mathematics is a restrictive science, might be somewhat incorrect. To me, mathematics is not for a restricted elite. Failure to understand and appreciate mathematics can lead to a lessening of the quality of one's life, be it understanding of the beauty of geometry, be it understanding how statistical surveys are conducted and what can be wrong with those, understanding notions about gambling situations, be they legal gambling or state-run gambling like the various lottos and those kind of things. But as I've always said, in effect to my younger students, that failure to understand mathematics will cost you money because there are people out there who will take advantage of that. And I believe that once you say to yourself, look, I can do this, there's no question I can do this, that 85% of the ability to do mathematics is based on your confidence. Now, some people would have you believe that mathematics is, again, is this very special area that only certain privileged people could understand. And to me, that is like the people who restricted the use of Latin during the Middle Ages. In the Middle Ages, only the certain elite, only the rare educated person would know Latin. And of course, all of the great scholarly works were written in Latin. Knowledge was in Latin. The Bible was in Latin. In fact, people who wrote the Bible in a local tongue, in many cases, were severely prosecuted. In some cases, they lost their lives because of breaking a rule. Because as long as a few people controlled the language of knowledge, then they controlled knowledge. And when you control knowledge, you control the ignorant. And it's my belief that we have many people who are ignorant mathematically, not because they couldn't do it, but because they were convinced, either verbally or non-verbally, that they just can't do it. I am amazed when I taught in the school systems, when I get parents who are proud to proclaim that indeed they never could do algebra, and look how successful they were. These same parents would never proclaim their great joy in saying that I can't read, I can't write. They would be embarrassed to admit that. But instead of being embarrassed about lacking knowledge of algebra, they were actually quite happy about it, and happy that their son or daughter was equally baffled by this area of mathematics. That is a very dangerous thing. In a previous lecture, we looked at the increase in the number of mathematical PhDs being issued by universities in the United States, and the severe decrease in the percentage of American citizens who are obtaining those doctorates in mathematics. We need mathematicians. We need people who are mathematically literate. And again, it is my hope that this tape, this Joy of Math tape, in some small degree can contribute to your improving your opinion of yourself mathematically, that you can expose yourself to new mathematical knowledge. So that, especially in our world, where technology is expanding at an ever-increasing rate, that is, the slope is increasing at an increasing rate, the knowledge of mathematics is vital for every single person, even to understand some scientific breakthrough, even to make a decision about whether or not the government should invest money in something like the Super Collider or traveling to Mars or what have you. It is very important that every person use mathematics and understand the mathematics in his or her vocation as well as avocation. What I'd like to do now is to quickly review some of the mathematics we've looked at in this series. We started with arithmetic, and here we see Leonardo of Pisa, Fibonacci, who represents the growth, the beginning of the growth of European arithmetic. Arithmetic is the result of thousands of years of human development. Its rules are not arbitrary as they might have seemed in fourth grade. They are based on both logical and consistent foundations. We have looked at the counting numbers, the whole numbers, which are the counting numbers plus zero, the integers, the rational numbers, the real numbers, and even the imaginary and complex numbers, which if looked at individually might be confusing, but when you realize they all are a stream of one area of mathematics, arithmetic, that began with the ancients, that began with scratch marks on caves and the building of buildings, and advanced slowly, of course, during the first millennium AD, but eventually caught up to the ancients, and where arithmetic is continuing to be developed, and of course we use that every day. Then we looked at algebra, and here is René Descartes, who in 1637 invented graph paper, which allowed us to be able to visualize algebraic functions, which led to the symbology that simplified the writing of those functions, which allowed scientists to examine and make models of the astronomical feats we observed, and eventually to use algebraic symbology to represent any real-world situation for which we can come up with some model, some function to represent it. And we developed now a powerful tool to describe our environment and the consequences of our actions. We talked about linear models and quadratic models and cubic models and exponential models, all of which can be used to represent different types of aspects of what we see around us. And we talked about slope, slope being how much y changes as x increases by 1, where x is now an explanatory variable, a measurement we will use to explain, and y is the response variable, a variable we will use to predict something, so that, for example, we can predict your college success based on SAT or ACT scores. So algebra is exceptionally useful, and is not something that you simply learn in high school or take in college, and that's it. Algebra is an exceptionally useful vehicle for solving problems and creating models. The generalization of slope led to calculus, and of course, here we see Leibniz, who does not get as much credit in the United States and other English-speaking countries as Sir Isaac Newton, but indeed is the co-discoverer or co-inventor of the calculus. And in fact, as mentioned in that lecture on calculus, it was the symbology that Leibniz developed that we use today in calculus. And calculus is basically a measure of change and the summative effect of change. And I think if people walking into their first calculus class who had the algebraic knowledge to deal with the manipulation of symbols and simply looked at the course as an intense study of change and the effect of change, might walk out with a different feeling about what they have learned. Because surely, except if you're an engineer or a mathematician or a computer scientist, much of what we do in calculus is really not that important. And in fact, if it is important, it can be done by a calculator or a computer. But to me, the deep understanding of change and the meaningfulness of change in our lives, both from day to day and in our society's life, is quite important, and calculus should get us thinking about change and how we measure change, and how change affects the future. Then we took a brief look at fractals. And if you'll allow me a little independence here, we're going to look once again at those fractal images that I find so fascinating, because every time I look at these images, I see something new. And again, this bursting of color in this image is magnificent. And the next image with its little spindly legs, and we know that if we blow up one leg, we see more spindly legs with little legs, and the little legs have even tinier legs, which we blow up are the same as the big picture. That is, these are self-similar. And here, this very delicate, almost like lace-like design. And again, remembering that all these designs are created by mathematics. There is no attempt by the mathematician, by the designer, to say, let's do something to create this design. Let's get something that has a big green eye in it with little things sticking out. No, we look at a mathematical function, use a computer to generate the image, and then, aha, we see something. And then the question is, if we change something just a little bit about the mathematics, how does that change the image? To me, here's an image that looks like a necklace. The person who created this did not start out to create a necklace. He or she simply took a mathematical function and used the computer to generate the image. A whirlpool of arms and these very lacy designs created mathematically. Another beautiful jewel-like image. And again, you look at it and almost stare into it and look in the inside and see what you see. And if you had the ability, you could blow it up and just look at the magnificence of what is created by mathematics. And here's another item that could look like a jewel, but again, to me, the key thing here, if you look into the centerpiece, you see that snowman with the head, where the head has a head, and where that head has a head, and the heads have arms just like the snowman's body. And again, an image of color, and the color is created by simply deciding on certain mathematical terms. I would certainly suggest that if you find this as exciting as I do, that you take a course, read a book or two, get a tape simply on fractals. Look at these images. Look at the color and the delicate nature and the specific nature of the design. And again, the repetition that using simple mathematics, we create very, very complex images. And finally, this image that looks sort of like a beetle. I mean, it's just phenomenal. And the symmetry of that beetle is absolutely amazing. And the next image, which obviously looks like some kind of jeweled tail, as if we had some scorpion. But if you'll notice, the jewels are gold and black, and they get smaller and smaller, but you know that when you blow them up, you'll see similar things. And all the little curlicues off of the jewels. The design, just a absolute magnificent design, strictly based on mathematics. We looked at geometry, and here's our old friend Euclid, who again, may or may not have looked like that. I don't believe we have any paintings of him, but this is possibly what he looked like. If he arrived today, he would come into our geometry classrooms and recognize exactly what we were doing, because he realized that geometry was a vehicle to learn logic, a logic developed by Thales hundreds of years before Euclid. And we use geometry every day when we are trying to be specific. It is probably the most concrete branch of mathematics. And then we had probability, and probability with the Bernoulli family contributing to looking at a study of uncertainty. This is critical in a world where uncertainty appears to be growing. The use of simulation gives us tools to obtain information about our uncertain world, and therefore we can make decisions based on the data obtained from these simulations. And as our technology, as our computer ability gets greater and greater, the possibility of what we can do with simulations is without end. We couldn't conceive of possibly simulations that will be modern, everyday occurrences 20 years from now. And finally, we talked about statistics. Statistics, a subject involving collection, display, and analysis of data. A subject that it really is a social science that uses a great deal of mathematics, not necessarily a mathematics of rules. In fact, we said that in statistics, there is no right answer. When you look in the back of the book, it says answer varies. This drives most mathematics teachers nuts. And in actuality, I know there are people out there who, when talking about statistics as a course they took in college, say sadistics. But as Florence Nightingale showed us, statistics is a vital science, one that allows us to gather small amounts of data, to make decisions based on those data, to make predictions based on those data, to compare things, be it a new drug medication, be it a new type of surgery, be it a new method of inspiring workers to be more productive, be it a new reform measure to reduce the return of prisoners to their prison cells when they are released, be it a opportunity to enhance the marketing of a new product or a service. All of these things utilize statistics, and statistics provides answers. It is not a cruel science, but a useful tool in interpreting the present and forecasting the future. Let us close our series with a review of the power of mathematics. Mathematics is a powerful language, and indeed it is a language, foreign to some, but it shouldn't be, because it is universal. It is a tool that is required if we are to solve the world's problems as well as our own individual problems. It allows us to represent complex ideas with simple symbols. And that, to me, is the key. We can take something exceptionally complex and in a few equations or formulas, in effect, bring that situation to an understanding. Models can be constructed to attempt to both explain and to predict. Simulations can be used to enhance our ability to define problems, to test solutions. Because in many cases, if we have identified a problem, we say, okay, what is the possible solution? Where should we do something? For example, an airline that was concerned about having too many people booked, but also concerned about having too many empty seats on flights, could simulate selling differing number of tickets based on the probability of a person who has a reservation showing up on time for the flight, and examine millions and millions of simulations to see which possible number of tickets sold for that particular flight would best satisfy both the flying public in terms of minimal overbooking and also satisfy the airline in terms of minimal lost profit from empty seats. Mathematics can be used to classify objects and concepts and to translate and to transport ideas. So that is why it's to be called a language. Basically, we can talk about using mathematics in the sciences, for example, in genetics, to learn about the transfer of characteristics from one generation to the next. The balancing of chemical equations to come up with an equilibrium situation obviously uses mathematics and provides information to solve problems in chemistry, make predictions in chemistry. Through the use of symbolic equations and systems of equations, we can model and attempt to control our physical world. So, for example, we are interested in the weather. And ultimately, I would expect that after we get around to solving all the other problems, human beings are going to attempt to better control the weather, especially weather that is destructive, tornadoes, hurricanes, violent lightning storms. And the initial attempt will be done through mathematical equations, attempting to quantify those factors that contribute to these violent weather, and then using possibly simulations to see how we can mathematically obtain information to reduce the violence or reduce the effects of this weather, and then actually go out and try it. The process of digitizing information, that is making information into actual numbers, allows rapid communication of all ideas, but specifically scientific ideas, so new science can be spread almost instantaneously among the scientific community members. Many of the technological advances in our medicine science would be impossible without the appropriate mathematics to test those advances, to ensure that we know if the new advance really, truly is worth the effort. Mathematics should be, and hopefully is, a source of pleasure to human beings. For example, games, and we all like games, and games are simply based on probability. If you knew you'd always lose, or you knew you'd always win, you would not play the game. But by basing a game on probability, and therefore adjusting the amount of risk you'd like in terms of the reward or consequence of winning or losing a game, the game becomes joyful. Geometric principles can give form and reality or abstraction to art. Obviously, we've talked about the use of geometry and perspective and other things having to do with great painting and sculpture. Mathematical knowledge allowed the ancients to produce harmonious sounds so that people heard the sounds and we created music. And in fact, there's a tremendous mathematical relationship between the harmonies of music, the instruments that play those notes, and how we create great symphonies and musical delights that provide us with pleasure, be it rock and roll or great classical or anything in between. It's all based on mathematics. Even our negative thoughts about mathematics can be sources of enjoyment through humor. A famous cartoon some years ago showed a person who had just passed away being greeted at the pearly gates. And the greeter said, "Your entry into heaven is based on your answer, your correct answer, to one question." The question is, a train leaves Chicago at a certain time, and at the same time, another train leaves Los Angeles heading in the opposite direction. Those of us who recognize that problem might have a good laugh and hope that that person had studied his or her algebra before entering the pearly gates. Thank you very much for your attention. Please find joy in math.